I am going to talk about image segmentation. What is image segmentation? Role or application of image segmentation. Different approaches for image segmentation, that is based on discontinuity and based on similarity. Different image detection operators, linking of edge points, local processing, global processing, which is also known as half transform. Then similarity based image segmentation, in which we are going to discuss about region going, region splitting, and automatic thresholding operations. Now, image segmentation is a process of subdividing an image into its constituent parts or objects in the image. So the main purpose of subdividing an image into its constituent parts is to extract some information, some meaningful information, so that the informations are useful for high level machine vision application. That is one of the most difficult tasks in digital image processing. So now we can say that image segmentation is nothing but a process of subdivision of an image into its constituent parts. So as you can see that in this image there is a person and there is a background. So we are going to segment this image into two parts. One is a background, another one is a foreground. Similarly, in the second image, we are going to locate the vehicles. So we are going to segment this image into two parts. One is a vehicle, that is a moving vehicle, and another one is a background. So you can see in this figure that we have located the vehicles and background. Similarly, in this third figure, we are segmented it into a background, that is a grass and horse. It has a various application in the field of medical imaging. You can see that this is a brain image in which we are locating the tumor. So we are segmenting this tumor in this brain image. Now, when we say the segmentation is nothing but a process of subdivision of an image into its constituent parts, so a question naturally arises that at which level this subdivision should stop. So you can see in this figure, there is a person who is seeing this football match. Then there is a ground. In the ground, there are some kind of cards are available, and then there is some written text. Then there is a texture of this ground. Then there are various audience that are present in this ground. So we can divide broadly. First, we divided this image into three parts. One is a person, then another one is a sports field, and third one is on the basis of audience. Now this person can be further divided on the basis of texture and face. Then this sports field can be divided on the basis of text. Then players that are present in the field, then curves, then the color of the field. Similarly, this ground or audience can be divided on the basis of the texture, on the basis of the person that are seeing these maps, and the texture basis also. So it is a completely application dependent. So where the segmentation should stop, that is decided by the person, and it is based on the application. So image segmentation is an initial and vital step in a series of process aimed at overall image understanding. So it can be divided on two parts. First one, a discontinuity based image segmentation, that is a partition of the image based on abrupt changes in intensity level or abrupt change in the gray levels of an image. Under discontinuity based approach, we are mainly interested in identification of isolated points or isolated lines or identification of edges. The next one is a similarity based approach. It means group of those pixels in an image which are similar in some sense. The simplest example in similarity based technique is a thresholding operation. In thresholding operations, if we have, for example, an 8-bit image whose intensity varies from 0 to 255, we decide a threshold level, for example, 100. So all the pixels have an intensity value greater than or equal to 100 will belongs to some region, whereas all the pixel whose intensity value is less than 100 will belong to another region. So thresholding operation can be used for image segmentation purpose. Similarly, the other example, for example, region growing starts from a particular pixel, then group all other pixels which are connected to this particular pixel. That means the pixels which are adjacent to this particular pixel and which are similar in intensity value or similar in some sense. The other approaches are region splitting and merging, so which we are going to discuss later on. So application of image segmentation includes identifying objects in a scene for object-based measurements such as the size and shape, identifying the objects in a moving scene for object-based video compression, identifying objects which are at different distance from a sensor using a depth measurement from a laser range finder, enabling path planning for mobile robots. So detection or image segmentation based on discontinuities. So several techniques for detecting basic intensity level discontinuities are point detection, line detection, edge detections. And common method of detection is a run a mask through an image, which we had already studied in image enhancement unit. Now, as you know that local averaging smoothness of an image. So if we are averaging some kind of, we are using some kind of averaging technique, then it will smoothen the image. That we have already discussed in image enhancement technique, that how we are going to use some kind of Gaussian filters to smoothen the image or median filter. So averaging is analogous to integration. So apparent a local change in intensity level can be detected using a derivative operations. For reason that will become evident shortly, first and the second order derivatives are particularly well suited for this purpose. So before discussing the discontinuity based image segmentation, we have to learn about what is derivative, first order derivative, and what is second order derivative in terms of image processing. So we obtain an approximation to the first order derivative at an arbitrary point x of a one-dimensional function fx by expanding the function into a Taylor series. For example, f of x plus delta x can be expanded as present in this expression. So as you know, in the case of image, since image is a discrete, so the minimum delta x or delta x is 1 because we cannot choose less than 1 pixel. So now delta x has been replaced with 1. So f of x plus 1 can be represented by this equation. So now if we are ignoring the higher terms, so f of x plus 1 can be written as f of x plus 1 is equal to fx plus del of fx by del x. So del of fx by del x is equal to f dash x, which is equivalent to f of x plus 1 minus fx. So this is known as forward difference. So similarly, we can take a backward difference. So in place of f of x plus delta x, we have to write f of x minus delta x, and delta x is 1. So for backward, f of x minus 1 can be expressed by this expression. Similarly, if we want a backward difference, then del of fx by fx is equal to f of x minus 1 so it will become f of x minus f of x minus 1, and if we are going to add this equation and this equation, so we will get a central difference. So del of fx by del x is equal to f of x plus 1 minus f of x minus 1 divided by 2. Now the second order derivative. For second order derivative, we are ignoring the higher orders that are present in this Taylor series. So we ignore all the higher order terms that is after the second derivative. So similarly, the second order derivative can be represented as f of x plus 1 minus 2 times of fx plus f of x minus 1. If we are using a, since this equation representing the one dimensional, if we are using a two dimensional, then for, if first we are choosing the y as a constant, so it can be represented as f of x plus 1 comma y minus 2 times f of x comma y plus f of x minus 1 comma y with this expression. And similarly in the second term, if we are choosing a x is a constant, so this can be represented del square f of x comma y, del y square can be represented by this equation. So as we know that in the case of Laplacian operator, which is del square f of x comma y is del square f by del x square plus del square f by del y square. So if we combine these equations, that will represent the Laplacian operator. Now, for example, I have taken this variation of intensity level. So now I'm going to measure the response of first derivative and second derivative. So as you know that the expression for the first derivative can be represented as f of x dash x is f of x plus 1 minus fx, and the second derivative can be represented as f of x plus 1 minus 2fx plus f of x minus 1. So now we are going to take the first derivative. As you know that it will be represented of f of x plus 1 minus fx for the first derivative. So now so this is the first derivative when we applied f dash on this fx. So we are going to get f dash x, and if we applied f double dash, then we are going to get a second derivative. So first order derivative must be 0 in the areas of the constant Gray level. So as we can see, this area is a constant Gray level. So we are going to get a 0 response here. Non-zero at the onset of the Gray level step or ramp. So if we are choosing the onset of the Gray level or onset of the Gray level step, so you can see here that it is non-zero. Similarly, at the onset of the ramp, it is also non-zero. Sorry, this one. So non-zero along the ramp, you can see here that this is a ramp. So the first derivative of this ramp is a non-zero. Now, if we applied a second derivative on this one, so second derivative is a 0 in the flat areas or a constant Gray level. So this one is a flat area or constant Gray level. So we are going to get a 0 response here. So 0 response here. Now non-zero at the onset and end of the Gray level step or ramp. So you can see here that at the onset of the ramp it is a non-zero. Similarly at the end of the ramp it is non-zero. So if we are going to see the performance of second order derivative on a step response, so you can see that it is at the onset of the step it becomes a non-zero, and and it is a 0 along the ramps of constant slope. So you can see that second order derivative is 0 along the ramp of this constant slope. So you can find here that it is a 0 along the ramps of constant slopes. Or you can see here this one is also a ramp of constant slope. So second order derivative response is 0. So now, as we have already discussed about the response of first order and second order derivative for this one. So we have taken the profile along this line, which is represented by this one. So here we can see that there is an isolated point here. So now, if we are going to take the first order derivative, so what we are going to conclude? The first order derivative is a non-zero at the onset and along the entire intensity ramp. So onset is this one, and along the this one is a ramp. So this is a non-zero along the onset, sorry, at the onset and along the ramp. So we conclude that the first order derivative produce a thick edge. So as you know that it will produce a thick edge because this one is a thicker. while the second order derivative is only non-zero at the onset of the ramp and zero along the constant slope of ramp. So as compared to first order derivative, second order derivative produce a so first order derivative is producing a thicker edge as compared to a second order derivative. Now second point is an isolated point. So this one is an isolated point. So if we are going to take a first order derivative, that it becomes minus 6. While if we are going to take a second order derivative, it becomes a minus 12. Similarly, here also you can see that the first order derivative gives a minus 2, while the second order derivative, the response is minus 4. So we can say that the second order derivative enhance the fine details, or it produces a stronger response corresponding to an isolated point. Now you can see that when we are moving from a darker region to a brighter region, or from brighter region to darker region, the second order derivative produces a two edges, while the first order derivative produces a single edge. So as we can see here, when we are moving from a darker to a brighter, then its sign changes from plus to minus. Again, when we are moving from a brighter to a darker, then sign changes from minus to plus. You can see here also that when we are moving from darker to a brighter, then the sign changes from plus to minus. So this double edge effect is an important characteristic that can be used to locate the edge. As we move into the edge, the sign of the second order derivative is used to determine whether the edge is a transition from light to dark or from dark to light. So in summary, first order derivative generally produce a thicker edge. Second order derivative has a stronger response to fine details such as thin lines, isolated points and noise. Second order derivative produce a double edge response at the ramp and step transition in intensity. And the sign of the second order derivative can be used to determine whether a transition into an edge is from light to dark or dark to light. Now in the next lecture we are going to discuss about image segmentation based on discontinuities.